requirements, and constraints for definite integration. Okay, so let's move on to a really important concept when we're dealing with definite integrals. As you recall from our previous discussions, we learned how to calculate a definite integral using the second fundamental theorem of calculus, often shortened to FTCII. Essentially, this theorem tells us that if we can find an antiderivative of a function, we can evaluate the definite integral by finding the difference in the antiderivative's value at the upper and lower limits of integration. But here's a crucial point. This powerful theorem isn't something we can just apply blindly to any function we come across. It's not a universal solution. There's a mathematical requirement, a precondition, if you will, that must be met before we can confidently use the formula we learned. Think of it like a recipe. You need the right ingredients and follow the instructions correctly, or it won't work. This slide is going to lay out exactly what that precondition is. We'll be looking at what makes a function eligible for using the second fundamental theorem and what happens if it doesn't quite fit the bill. In the following slides, we'll explore this condition in detail with examples, so you'll know exactly how to check and what to do if a function doesn't meet the criteria. The fundamental requirement, continuity. Okay, so let's delve a bit deeper into why the second fundamental theorem of calculus, or FTCII as we've been calling it, isn't always applicable. As we discussed on the previous slide, it's not a fundamental formula. This slide outlines the crucial requirements a function must meet before we can confidently use it. The core idea is this. For the second fundamental theorem of calculus to be valid, the function we're integrating, we represent that as f of x must be both well-defined and continuous across the entire closed interval from a to b, written as a, b. Remember, a closed interval includes the endpoints, a and b. Now, let's break down what well-defined and continuous actually mean. First, well-defined. This simply means that if you plug any value of x between a and b into the function f of x, you must get a real and finite number as an output. Think of it like this. The function can't break or give you an error. Common issues that make a function not well-defined include dividing by zero, because division by zero is undefined, or trying to take the square root of a negative number, which results in an imaginary number, not a real number. If either of those happens within our interval, the function isn't well-defined there. Next, let's look at continuity. A continuous function, in simple terms, is one you can draw without lifting your pen from the paper. There are no sudden breaks, jumps, or gaps in the graph. A more formal way to put it is that there are no vertical asymptotes. Within the interval from x equals a to x equals b, a vertical asymptote is where the function shoots off towards infinity, creating an infinite discontinuity. So, imagine a smooth, unbroken curve from x equals a all the way to x equals b. That's what we need for continuity. Finally, and this is really important, if a function fails either of these conditions, if it's not well-defined or it's not continuous, at any single point within the interval a, b, then applying the standard integration formula, integral from a to b of f of x dx equals f of b minus f of a, is mathematically incorrect. You'll get a wrong answer. We'll see this illustrated with a specific example in the following slides, but it's vital to understand this prerequisite before you start calculating. Real-world analogy, the unbroken bridge. Okay, let's move on to slide 3. This slide uses a real-world analogy to help solidify the concept we've been discussing, the requirements for using the second fundamental theorem of calculus, or FTCII. Imagine you are tasked with measuring the total distance of a bridge from point A to point B. Think of this as analogous to finding the definite integral of a function between two limits. The second FTC is like a formula that calculates the distance based on the starting and ending coordinates. Essentially, it allows us to find the total area under the curve, or in this case, the total distance, by evaluating the antiderivative at the endpoints. However, this formula only works if the bridge is physically intact. If there is a massive gap or a collapsed section in the middle of the bridge, you cannot simply subtract the start coordinate from the end coordinate to find the walkable distance. the path is interrupted. You'd need to account for the missing section, perhaps by finding an alternate route or acknowledging the discontinuity. Similarly, in integration, a discontinuity, a point where the function is undefined or has a jump, acts as a gap that prevents the standard theorem from working. If our function has a break within the interval we're integrating over, applying the FTC-II directly will give us a wrong answer. This analogy is crucial because it helps us visualize why continuity is so important. We'll see in the following slides how to identify these gaps in a function and what that means for our ability to use the second fundamental theorem. Remember, we need a smooth, unbroken bridge or a continuous function for the theorem to be valid. Detailed example analysis. Okay, so far we've established that the second fundamental theorem of calculus, or FTC-II, is a powerful tool for evaluating definite integrals, but it's not something we can just apply blindly. Remember from the previous slides, we said there are requirements, specifically, that the function we're integrating needs to be continuous over the interval we're integrating over. Now, let's put that into practice. On this slide, we're going to look at an example where the FTC-II doesn't work directly, so you can see what to watch out for. We're considering the definite integral of x times the quantity of x squared minus 1, all raised to the power of 1/2, with respect to x, evaluated from -2 to 3. Let me say that again more mathematically. The integral from -2 to 3 of x multiplied by the quantity x squared minus 1, all under the radical sign, with respect to dx. Now, a common mistake students make is to immediately jump into finding the antiderivative of this function. You might think, okay, this looks like a good candidate for a u substitution, and you'd be right, you could find an antiderivative. And then, you might be tempted to simply plug in the upper and lower limits, 3 and -2, into that antiderivative. However, before we do any of that, before we even think about finding the antiderivative, we must first check if our function actually meets the requirements for using the second fundamental theorem. We need to verify if it's continuous and even well-defined across the entire interval from -2 to 3. That's what we'll be doing in the following steps. So, hold off on the antiderivative for now. Let's do a little bit of pre-integration checking first. Step-by-step analysis of example. Okay, so let's continue with our example. As we discussed on the previous slides, we need to verify if the conditions for applying the second fundamental theorem of calculus are met before we attempt to evaluate the integral. Remember, blindly applying the formula will give us a wrong answer if those conditions aren't satisfied. Now, let's look at this slide. It breaks down the analysis step by step. Step 1, identify the function. This is pretty straightforward. The function we're dealing with, the part inside the integral sign, is f of x, and it's given as x multiplied by the quantity x squared minus 1 raised to the power of 1/2. We can also write this as x multiplied by the square root of x squared minus 1. It's just a different way of representing the same thing. Step 2, determine the domain of the function. This is where things get a little more careful. The domain of a function is simply the set of all possible x values for which the function produces a real number output. In this case, we have a square root. You'll recall that the square root of a negative number isn't a real number, it's an imaginary number. Therefore, to ensure our function remains within the realm of real numbers, the expression inside the square root, that's x squared minus 1, must be greater than or equal to 0. So we set up the inequality. X squared minus 1 is greater than or equal to 0. Now, let's factor that quadratic expression. We can rewrite x squared minus 1 as the product of two binomials. X minus 1 multiplied by x plus 1 is greater than or equal to 0. To solve this inequality, we need to consider where each factor is positive, negative, or 0. Doing so, we find that this inequality holds true when x is less than or equal to -1, or when x is greater than or equal to 1. This means the function is only defined for values of x that are either less than or equal to -1 or greater than or equal to 1. Keep this in mind, because in the next step, we'll compare this domain, the values of x where the function is defined, with the interval over which we're trying to integrate. That comparison will tell us whether we can safely apply the second fundamental theorem. Comparing domain with interval of integration. Okay, let's move on to step 3, where we compare the domain of our function with the interval we're integrating over. Remember, we've been carefully checking if we can actually use the second fundamental theorem of calculus. So, the interval of integration, that's the range of x values we're looking at, is from -2 to 3, written as -2, 3. This means we're considering all the numbers between -2 and 3, including -2 and 3 themselves. However, in the previous step, step 2, we figured out the domain of our function, f of x, which was x times the square root of x squared minus 1. We determined that this function isn't defined for values of x between -1 and 1. In mathematical terms, the function is undefined for any x within the open interval -1, 1. Let me illustrate with an example. If we try to plug in x equals 0 into our function, f of 0, we get 0 times the square root of 0 squared minus 1. That simplifies to 0 times the square root of -1. Now, the square root of a negative number isn't a real number, it's an imaginary number. Since our function produces an imaginary result at x equals 0, it's not well defined at that. This is crucial because our interval of integration, -2, 3, includes values between -1 and 1, where the function is undefined. And as we discussed in the earlier slides, the second fundamental theorem absolutely requires the function to be well-defined and continuous across the entire interval of integration. We'll see in the next step what this means for our ability to actually calculate the definite integral. Conclusion of example analysis. Okay, let's wrap up our analysis of this example. This slide presents our final conclusion. So, step 4, conclusion. As we've carefully established, the function f of x, which was x times the square root of x squared minus 1, is not well defined and is not continuous across the entire interval from -2 to 3, that is, the interval -2, 3. Remember from earlier, we determined it's undefined for values of x between -1 and 1. Because of this lack of continuity and being well defined, we can definitively say that the second fundamental theorem of calculus simply cannot be applied directly to evaluate this integral. Think back to what we discussed at the beginning. The theorem has a precondition. That precondition, continuity, isn't met here. Therefore, any attempt to find the antiderivative, let's call it f of x, and then calculate f of 3 minus f of -2 would be mathematically invalid. You would be getting an incorrect answer, and the method wouldn't be legitimate. Now, this doesn't mean the integral doesn't have a value. It just means we can't use this straightforward antiderivative method to find it. We might need to explore other techniques, like splitting the integral into multiple integrals at the points of discontinuity, which we'll cover in future lessons. But for now, the key takeaway is recognizing when the second fundamental theorem isn't applicable. In the next slide, we'll look at some common mistakes students make with these concepts, so you can avoid them in your own work. Common mistakes. Okay, let's move on to slide 8. This slide highlights some common mistakes students make when dealing with definite integrals, and it's really important we address these before you move forward. Blind application. The biggest mistake we see is students just jumping right into using the formula for the second fundamental theorem of calculus. That's integral from a to b of f of x dx equals f of b minus f of a without first checking if the function, f of x, is actually continuous on the interval from a to b. Remember what we discussed on the previous slides. Continuity is a requirement. You can't just apply the formula hoping it works. You must verify the conditions are met. It's like trying to build a house on a shaky foundation. It's going to collapse. Ignoring asymptotes. Another frequent error is overlooking vertical asymptotes. Let's look at an example, the integral from -1 to 1 of 1 over x squared dx. Now, what happens at x equals 0? Well, 1 divided by 0 is undefined. This means we have a vertical asymptote at x equals 0, which falls within our interval of integration, -1 to 1. If you were to blindly apply the formula, you'd get a numerical answer, but it would be completely wrong. The function essentially blows up. It goes to infinity at that point, and our theorem simply doesn't apply. Think of it like trying to measure the area under a curve that has a hole in it. The standard formula won't give you the correct area. Assuming domain is always R. Finally, students often make the mistake of assuming that every function is defined for all real numbers. That's not true. Always check the domain of your function. Remember, the domain is the set of all possible input values for which the function produces a real output. Be especially careful with things like square roots. You can't take the square root of a negative number and get a real result. Also, watch out for denominators that could be 0. These situations will restrict the domain and potentially make the function undefined at certain points, which, as we've established, breaks the continuity requirement for definite integration. So keep these common pitfalls in mind. Before you even think about applying the second fundamental theorem, take a moment to check for continuity, asymptotes, and the overall domain of your function. This will save you a lot of frustration and ensure you're getting accurate results. In the next slide, we'll summarize these key takeaways to solidify your understanding. Key takeaways. Okay, let's recap everything we've covered regarding the requirements for using the second fundamental theorem of calculus, or FTCII. This slide summarizes the key takeaways, and it's crucial you understand these points before attempting any definite integration problem. Here's a breakdown. First point, continuity is mandatory. The second FTC requires f of x to be continuous on the closed interval a, b. Remember, we established that the FTCII isn't a magic formula you can apply to any function. It relies on a fundamental condition, continuity. What does that mean? It means the function, which we're calling f of x, needs to have a smooth, unbroken graph across the entire interval we're integrating over. The closed interval a, b means we include both the endpoints a and b in our consideration. No gaps, no jumps, no vertical asymptotes are allowed within that interval. If there is a break in the graph, the theorem simply doesn't hold. Next, check the domain. Before integrating, ensure the function is defined for every x in the range a, b. This is closely related to continuity, but it's a separate check. The domain of a function is all the possible input values, the x values, for which the function produces a real number output. Before you even think about finding an antiderivative, you must verify that your function is defined, meaning it gives you a valid, finite answer for every single x value between a and b inclusive. Think about things that could make a function undefined, like dividing by 0 or taking the square root of a negative number. Finally, invalidity. If there is a point of discontinuity or an undefined region within the limits, the standard f of b minus f of a method fails. This is the consequence of ignoring the first 2 points. If you find that your function is not continuous or is undefined anywhere within the interval from a to b, then directly applying the formula, where f of b represents the antiderivative evaluated at the upper limit b, and f of a is the antiderivative evaluated at the lower limit, a, and you subtract the latter from the former, will give you a wrong answer. It's mathematically invalid. Remember our example with the square root function. We saw how the function wasn't defined for certain values within our integration interval, and therefore we couldn't directly apply the FTCII. These takeaways are your safety net. Always check for continuity and domain before you integrate. It will save you a lot of frustration and ensure you get the correct results.